Welcome everyone to Calculus BC. In today's episode, we're going to be discussing chapter 7.6, which is improper integrals. This integration technique will be the last integration technique we need for the Calculus BC exam. And basically, all improper integrals boils down to is this is integration against an asymptote or some type of infinite behavior. Typically an asymptote, but sometimes that asymptote won't always be obvious, and you'll see what happens when we get to those problems there. So in order to understand this idea, why don't we go ahead and first start off with a function that we know very, very well. We'll start off with y equals 1 over x. And it's a pretty basic function. I mean, we know that it has infinite behavior. We know it has infinite behavior that leads to a number, right? We know that if we took the limit as x went to infinity, in this case positive infinity, of this function, we know we would get 0. We know that this function is decreasing, right? We know that this function is decreasing, right? And so the question is that if we were to integrate this function against the asymptote of its end behavior, would there be an area that we can find? Now, right now, it seems like probably, right? I mean, it looks like, the limit as x goes to infinity of this function would go to 0. Functions' values are always decreasing, which is why this limit seems to hold true. And if we were to graph this thing, and again, we're just looking at from the positive side, right? Because we're looking at x going to infinity here. It looks like this thing would head closer and closer to 0. And if I were to take the integral from, say, 1 to infinity of this function 1 over x dx, it seems like I'd probably get something, right? I mean, this limit goes to 0, which means I'm probably going to get like some finite number, right? And that seems to be a pretty good intuition if we were to just guess without knowing anything else. The way we're going to attack this problem is we are going to actually, because we can't actually get to infinity, right? We can't plug in infinity as an upper bound of integration because we don't actually have infinity in the palm of our hands. We have to bring back an old tool that's going to allow us to approach infinity infinitely closely. And if you're wondering what that is, you've guessed it. We are bringing back the limits. So the way I'm going to attack this problem is I'm going to assign infinity to become k. What that allows me to do is it allows me to take the integral from 1 to k now, but behind that integral is going to be the limit as k goes to infinity. So what I'm doing is I'm allowing my integration to approach infinity infinitely closely. And I'm going to go ahead and do 1 over x dx, and I'm going to go and integrate this thing like any other definite integral, actually. So I'll go and just call him ln of, in this case, x. And then that's going to be on the interval from 1 to k, and this is the limit as k approaches infinity. And that's going to get me, again, the limit as k approaches infinity of ln of k minus ln of 1. This guy goes to nothing. Now, the limit as k approaches infinity of ln of k, well, if we know this graph really well, this graph looks like this. And even though it grows really slowly on its end behavior, it still grows, which means this guy is going to approach infinity as k approaches infinity, which is why we classify this type of integral as what we call a divergent integral. You're going to want to get used to that word. We're going to hear more of that word after we approach the midterm when we get into something called sequences of series. But yeah, this integral diverges. So you can write diverges or divergent, but basically what that means is that the area would actually explode into infinity. Now, if you're wondering why that is, it's a really good question. Well, what happens if you start off here at 1 is you have a bunch of area here, and then as you go down the curve, you do accumulate less and less and less area. And while this function's individual values approaches 0, right, as we saw in the limit right here, right, the individual values approaching 0, remember, the integral is a summation of a Riemann sum, right? It's the limit of a Riemann sum where the Riemann sum is taking a bunch of infinitely thin rectangles and calculating their area, which means that as you approach infinity, the values of the rectangles get small, but they don't get small fast enough so that you can have some type of discernible sum, which is kind of an interesting thing because you figure if the values themselves are approaching zero, why can't the area approach zero? But remember, the values need to converge or get small fast enough. And I'm going to bring that up again many, many times throughout the class. If the terms do not get small fast enough, you're going to end up with this divergent situation as we see here. So why don't we go ahead and move forward into the next example, and we'll see if this one actually does converge towards an answer. In this next example, I'm going to be doing almost the exact same function, except it's going to be 1 over x squared, and I'm going to integrate from 1 to infinity. I'm keeping the examples kind of light right now. We will get to some harder ones in a little bit. But again, we'll do the exact same thing. We're going to do the limit as k approaches infinity of the integral from 1 to k, and I'll go and call them x to the negative 2 dx. Well, that's going to be the limit as k approaches infinity of negative x to the negative 1 on the interval from 1 to k. Now I'm going to do a couple things here. I'm going to pull this negative all the way outside the limit just because I really don't like those constants in there. And then I'll probably flip him back over into x to the negative 1 power. So what I have is I've got the limit as, not x, as k approaches infinity with the negative on the outside of 1 over x on 1 to k. And now I'll go and plug the values in. So I've got the negative limit as k approaches infinity of 1 over k minus 1 over 1. Now I'm in a bit of a different situation here. If I let k go to infinity, this entire expression actually goes to 0, right? Because 1 divided by the biggest thing we can think of is something super, super small, which gives me the negative 1 that results from the minus 1, but the negative on the outside comes in and negates that 1, or negates that negative 1, giving me 1. So it seems like right now the 1 over x squared does in fact converge fast enough in terms of its individual terms. The individual terms get small faster than the 1 over x, which we saw up here, which produced a divergent result. The convergent result towards 1 is the result of x being squared now. So yeah, again, I'm just kind of going back to that idea of getting smaller fast enough, right? That's super, super important. I'm going to come back to that multiple times throughout the course of this semester. So I'll be right back again with another example. In this example here, and I'm pretty sure you're going to be able to predict pretty clearly about what this is going to do. I'm going to have Ordinarily, I would have you guys doing this on your own, so if you want, feel free to pause the video, try this one out on your own, and see what happens. I'm going to go ahead and move forward with it. If you've already paused, then here comes the answer to this question here. We're going to integrate from 1 to infinity of 1 over root x dx. Again, I'm hoping you'll have a general intuition as to what this thing's going to do based off of what this guy did. 1 over x, what did he do? Versus 1 over x squared, what did he do, right? We're going to try and figure out what does 1 over rad x do as we approach infinity on its integral. So the limit, again, as k approaches infinity of the integral from 1 to k, I'll just call them x to the negative 1/2 dx. That's going to be the limit as k approaches infinity of, looks like, x to the 1/2 times 2 on 1 to k. Just like I did with the negative, I'm going to go and kick that 2 outside of the limit. So what I've got is 2 limit as k goes to infinity of x to the 1/2 on 1 to k. And as you can probably see, your prediction, if you had one, is probably coming true at this point. This dude very much looks like he's going to diverge. So if I do 2 limit as k goes to infinity of k to the 1/2 minus 1 to the 1/2. Of course, 1 to the 1/2 is just going to be 1, but obviously as we take the square root of something that's approaching infinity, we're going to get some type of infinite behavior. This thing is divergent, and I'm hoping that you saw that coming. So hopefully we're starting to establish a pattern here as to what diverges as a sum, what converges as a sum, to the point where I'm going to give you one here. I'm not going to do it, but I'm going to have you just predict like what's going to happen here from 1 to infinity of 1 over x to the 4th dx. And again, we'll come back to him in just a second here, but I just want you to take a second and predict what do you think that's going to do. And I don't need you to know. I don't need to know what the result of the integral is, but I just want to know what you think. If it's going to converge or is it going to diverge? Just think about that for a second. I'll be right back with something different in a little bit. I'll be back. So at this point, you might be wondering, what does converge fast enough even mean? And it's a really good question. And basically what it boils down to is, do the individual terms get small fast enough to allow for the sum of the areas, the individual areas, to approach a discernible number rather than explode into infinity like we saw with the 1 over x and the 1 over rad x example. We want them to behave, if we're going to look for something that converges, we want something to behave more like 1 over x squared that would actually produce a value of 1, right? And so what we're going to do is we're going to try and prove something here. We're going to prove the notion of what it takes to allow for a function that's rational like that to converge. Now, not every improper integral is going to be rational like that. We're going to actually deal with one in a little bit that is not, but we'll save that for a little bit later. Right now, what I want us to do is I want us to find a value of p such so that the integral will converge. So that the integral will converge. And so what does that even mean? So what I'm going to do is I'm going to say, okay, I'm going to go ahead and just take the integral from, let's say, some value. It doesn't even really matter what it is, but we've been using 1 this whole time. I'll go and keep on using 1. And I'll go to infinity of 1 over x to the p power. Now, it's important to know p is a constant. So that means when I integrate this thing, there's not going to be any kind of weird log rules or anything going on. P is a number. And so I'm going to go ahead and say, all right, well, then this is the limit as k approaches infinity of 1 to k. I'll go ahead and just call them x to the negative p dx. And again, just a reminder, p is a constant. That way we're not, again, no log rules here. No, we're not doing anything crazy. This is just going to be the limit as k approaches infinity of, looks like x to the, and again, if we were just dealing with a constant here, we would just add 1 to it. So this is going to be negative p plus 1 over that exact same exponential power. So it'll be over p plus 1, and that's going to be on the value from 1 to k. And again, the reason why the bottom limit of integration doesn't matter is because it's just going to be a constant anyway. Whatever we get out of the leading term of integration, we're just going to add that to x to the whatever power anyway, so it's not really going to be of consequence. We just want to know if something will converge or something will diverge. That's all we're trying to find. So I'm going to go and plug the k in. Now, it's important to know I am plugging the k in for x, right? This is a dx integral, so I am not plugging in for p. All right, so please make sure we keep that in mind. This is going to be k to the negative p plus 1 over negative p plus 1 minus, again, I'm plugging in for x, not p, so 1 to the negative p plus 1 over negative p plus 1. And that is still the limit as k approaches infinity. So now we're going to stop right here at this step, and what I want to ask is, this constant here, we don't care about him. He's just going to stay constant, so if he's there or he's not, it's going to be of no consequence for our convergence. What I really want us to pay attention to is this portion right here. Because if this portion here were to explode into infinity, we would diverge, but we don't want that. We want this to converge. So there's only one way that that could possibly happen. The only way I can get a fraction to converge would be if the numerator was not as big as the denominator, right? As k went to infinity, if this thing could just somehow go to 0, that would be a way to get convergence. That way the constant is left over. We've got a number, no more infinite behavior because the infinite behavior caused something to disappear. So how do I do that? If you want, please feel free to pause and think about that picture real quick, to think about what is it that needs to change about that fraction. Look at it really hard. So I'll hit the pause button. If you're done hitting the pause button, go ahead and come back to us. What we want to have happen is we want this numerator, this k, we want him to jump to the bottom. Why would we want that? It's because k is the one going to the infinity. So if I could somehow force the k down to the denominator, we could force this thing to converge. How do I force any kind of constant or anything at the top to go to a denominator. Well, hearkening back to integrated 1, as long as the exponent was negative, then that constant would then jump down to the denominator and we would then converge to 0, at least in terms of the first term. So how do I make sure that the k value will actually do that? Well, the negative p plus 1 part is going to have to be negative. In other words, he'll have to be less than 0. Notice how it's not less than or equal to, because an equal to exponent will make the base just go to 1. We don't want that. We want this thing to be smaller than 0, right? And so I'm going to go ahead and just add p to both sides. So that means that 1 is going to have to be less than p, or more generally speaking, p will have to be greater than 1. So if you look at all of the other integrals that we've done at this point, right? If we did the integral from 1 to infinity of 1 over x dx, notice how that diverged, right? Notice how that diverged. But the 1 to infinity of 1 over x squared, that converged, right? And notice how the p-value, right, which is the exponent that is attached to the x, that too is in fact bigger than 1. So I'm pretty sure that follows what this pattern is telling us. Similarly, how the 1 over rad x dx is really 1 over x to the 1/2 power underneath the integral. Of course that's going to diverge. We should have seen that coming even without knowing this rule. So a while ago I asked you to make a prediction about the integral from 1 to infinity of 1 over x to the 4th. And again, we're not really going to look for its actual integrated value, but we're going to look and see if it's converging or diverging. Well, you can look straight up at the 4. Greater than 1, this thing's going to converge. We will find a discernible answer. This thing's not going to explode into infinity on us. So hopefully that makes sense. I'll be back with the next couple of examples, because after this, it's just drilling. In this problem, I want to talk about what happens when the asymptote is not clear. And so this one seems to be a pretty standard operating procedure integral until you realize that the lower bound of integration needs to, in a sense, get plugged in, quote unquote, into this function here. And if you know what this thing looks like, you know that there's a vertical asymptote at 0, and he just shrinks a little bit faster than a normal 1 over x. And so you are still integrating against an asymptote, even though the behavior isn't going to infinity explicitly. You have to understand that it's going to infinity implicitly. And so the change in this problem is nothing. You just have to be aware of where the infinite behavior is. So what we're going to do now is we're going to take the limit as k goes to now 0 from the right, because 0 is the one that's producing the infinite behavior, and it's going to be the integral now from k to 3. And it's going to be x to the negative 2 dx. And I keep using these examples just because I want to have you see them in different ways. So from here, this is going to be negative x to the negative 1 on k to 3. Again, limit as k goes to 0 from the right. Same thing as always. I'm going to kick this negative all the way on the outside the limit. Negative limit as k goes to 0 from the right of 1 over x on k to 3. That's k. And so now from here, I've got 1 over 3 minus 1 over k, and that's the negative limit as k goes to 0 from the right. Now, if you notice really carefully, this thing here, as you approach 0 from the right, this thing's going to diverge here. So what you've got is essentially 1/3 minus an infinitely large number, and that means that once a piece of this diverges, the whole thing diverges. Now, I know what you're thinking. Wait a second, you just told us that when the p-value is greater than 1, you would be convergent at all times. But remember, in that situation, the k value was approaching positive infinity, which means we were looking at this end of the graph. What that means about this one is that as you shoot up towards the positive infinity, that is on the y side, the values are not approaching the y-axis fast enough. There's that term again. Not approaching the y-axis fast enough to produce a coherent sum. That's why this thing diverges. It explodes out to infinity. So hopefully that makes sense. I'm going to be back with another example when we have asymptotes on both sides. And how do we deal with that? So in this example here, we're dealing with infinite behavior on both sides. And so we're going to see what happens to this type of function. Now, this function here is a multifaceted problem. It deals with infinity on top and bottom, so we're going to have to first split apart this improper integral and deal with two improper integrals. But then there's going to be another step in here that you're going to not want to see. But it exists in here. So this is, again, a multifaceted problem, so make sure you're not skipping too much about this. Because we're dealing with infinity on both sides, we're going to actually have to do two separate improper integrals. So what I'm going to do is I'm going to first off say the limit as k approaches negative infinity of the integral of k to, now I want some discernible number. It doesn't really matter where you decide to break off this integral, as long as you split it off somewhere. I'm going to go and just choose 0, because 0 is kind of a nice halfway point between negative infinity and infinity. And so I'm going to go and just do e to the negative x over 1 plus, now I'm going to write this a little bit differently, and I'm hoping that you'll see what the technique that I'm going to have to do here is. And I know you're hoping that it's not that, but it really is that. And now I'm going to go ahead and say, all right, well, what is this? This is plus, again, another limit, and I'm not going to call it k, because k is going to negative infinity. I'll go and just say as n goes to infinity. And I broke off at 0, so I'll go and just start up again at 0, and as 0 goes off to n, same function, e to the negative x over 1 plus e to the negative x squared dx. Now, important thing to note, and that is that if either one of these things diverges, the whole thing diverges. I'll type that in. If either one diverges, the whole thing diverges. So if we can find divergence in one of them, then that means that the entire thing shoots off to infinity. Whether you're adding or subtracting, whatever, it doesn't matter. So we'll see what happens here. Now, if you're wondering what that move is that I keep thinking that you're trying to avoid, it's going to be this one. This problem is a u sub, and that is why I wrote the e to the negative x on bottom the way I did. One thing about doing a u sub on an improper integral like this is that we're already doing a lot of replacements of the limits of integration. So I don't think I'm going to be replacing my limits of integration in terms of u, similar to how we did it in integration by parts. With that said, I am not going to write down the limits of integration in terms of x or k or n when I do my u sub. What I'm going to do is on the side here, I'm just going to do a little bit of side work, and I'm going to say u equals e to the negative x, du is equal to negative e to the negative x dx, which means negative du equals e to the negative x dx. This would be my linkage right here. And again, this u sub will work for both integrals, so I only have to do it once. So what I've got here is I've got the integral of, I'll slap the negative on the outside here, 1 over 1 plus u squared du, which then becomes negative inverse tangent of u, which really is negative inverse tangent of e to the negative x. Once I've found that out, then my improper integrals will just transform into what I need them to transform into. So what I've got is I've got the limit as k goes to negative infinity of, I'll go and slap the negative all the way outside here, tan inverse of e to the negative x on k to 0, and then it's going to be plus this one, again, another negative limit here. And of course, the plus and the minus will become minus, but I do want to make this a little more methodical. N going to infinity of tan inverse of e to the negative x, not dx, on, looks like 0 to n. Now I'm going to go ahead and plug all of this stuff in, and I think I'm going to run out of space, so give me 1 second. I'm going to make some more space here. I'll be right back. And I am back. I'm at the top of the board again, so we have enough space for this. So now I'm going to just go and evaluate this thing. So now I've got the negative, so limit as k goes to negative infinity of, looks like tan inverse of e to the 0 minus tan inverse of e to the negative k. And I'm going to go and leave it like that for now, and then we'll see how we evaluate it, because I think something interesting is going to happen here. So from here, now I'm going to have this plus and minus turn into minus, and I've got the limit as n approaches infinity of tan inverse of, looks like, I'll go and call him, instead of e to the negative x. I'll call him 1 over e to the n. And I hope you understand why I'm doing that, because n's approaching positive infinity here. And then minus tan inverse of e to the 0. Okay, there's a lot going on here. So at this point, I feel like we're in a safe place to just kind of let the limits happen individually. This is going to become tan inverse of 1, because e to the 0 is 1. This is going to become tan inverse of e to the, looks like as x approaches, well, I'll just go ahead and call him still e to the negative k. I'll go and just keep my limit here because I want to talk about him in a little bit here. Limit as k goes to negative infinity, because there are certain values I can get, certain values I want to let the limit happen on. So from here, this is going to be, I feel like this here I can go and kind of let the limit happen. This is the one I really want to talk about, the k going to negative infinity. As n goes to infinity here, this inside of the tangent is going to turn into 0. So what I've got is tan inverse of 0 minus tan inverse of, looks like e to the 0 is 1. So we'll just go and call him that. Okay, this guy. So as k goes to negative infinity, I've got e to the negative k. So this is really negative k. So as k gets really, really large, what happens with tan inverse is I'm going to end up with tan inverse of very large, right? Very large. Now, if you know what the tan inverse graph looks like, then the tan inverse of very large actually leads us to our good old buddy pi over 2. So hopefully that makes sense. This tan inverse of 1 is going to be pi over 4. That's one thing, minus tan inverse of 0 is 0. And then tan inverse of 1 is pi over 4. So what we can do is we can go and just combine some like terms here. And I almost forgot, I have got a negative hanging out there, so I will go ahead and put him in there. So the negative will distribute in. I got negative pi over 4 plus pi over 2. Looks like a negative and a negative will become positive pi over 4, which means these guys will cancel each other out, leaving me only with pi over 2, which is interesting because you figure the, integral from negative infinity to infinity of a really complex looking function gives you pi over 2. The summation of the areas underneath, from negative infinity to infinity gives you an actual number. It's kind of cool. So hopefully that makes a bunch of sense to you. And I think that will wrap it up for this episode. When it comes to improper integrals, please remember the other integration rules can still apply. So we did one just now that encompassed improper integrals as long as with a u sub. And there are ones that incorporate by parts. And so there are ones that incorporate partial fractions. So it's just integrating against an asymptote, against some type of infinite behavior. So the other integration rules will definitely apply. With that said, hopefully this makes enough sense. As always, please leave comments or questions in the comments area. Congratulations, everyone. You have now finished Chapter 7. You know all of the integration techniques you're going to need to know for the AP exam. Stick with us. We will be back with Chapter 8 when we revisit an old friend, differential equations, slope fields, and we will introduce a new friend, Euler's method, and we will get onto that. And as always, thanks for hanging out. I will see you all in the next episode.